Hi everyone, this is your struggling CS student. Today, let's take a look at another LeetCode daily problem. Oh, it's taking a while to load, huh? Okay, today's problem, LeetCode 1415, the k lexicographical string of all happy strings of length n. So what does that mean? So a happy string is a string that consists only of letters of the set A, B, C, K, where s of I is not equals to s of I plus 1 for all values of I from 1 to s of s dot length minus 1, and the string is one index. Okay, so this just means that the current character is different from the next character. Okay, so for example, the strings a, b, c, a, c, b, and a, b, c, b, a, b, c, blah, 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 all happy strings, and a string. So basically, you can't have any consecutive characters that are the same. So given two integers n and k, consider a list of happy strings of length n sorted in lexicographical order. Return the kth string of this list, or return an empty string if there are less than k happy strings of length n. Okay. Mm. So happy string only has the letters A, B, and C. Given to consider a list of all happy strings of length n sorted in lexicographical order. Return the kth string of this list, or return an empty string if there are less than k strings of the length n. Okay. CAB, there are 12 different happy strings of length 3, ABA, ABC, ACA, okay. So the constraints are n is less than equals to 10, and k is less than equals to 100, okay. So, well, I've solved this problem in the past, and I kind of remember the problem. And looking at the constraints, well, n is only less than equals to 10, which means what? We only care about strings whose length is at most 10. So, well, if you know the constraints, then what you can do is you can generate all of the valid combinations. Not sure if combinations is the right word, but you can generate all the valid strings of length n in a lexicographical order, and on the kth string that you generate, you can then return the result. So I hope that makes sense. We can work through an example. So if let's say n is equals to 3 and k is equals to 9, right? And we're only given the only characters we care about are A, B, and C. Then what happens is, starting from the empty string, you will say at this point, the lexicographical smallest string that you can possibly generate is, you can put an A here. Then from here, what are the options that you have left? You only have B and C, right? But of course, we can do it in a greedy manner and say, hey, we go B first, then we go C next. Once we go B, when we put B here, maybe I should do it like this. Once we put B here, what is the next best character that I can put? And the next best character is actually you can put back A again. And this is the first string with length n, where n is equals to 3 that we generated. So the next one that we can generate will be A, B, A, B, C, A, C, A, and A, C, B. Let's see if that's correct. I hope I didn't make any mistakes. And then you just keep going from there, right? So it's ABA, ABC, ACA, and ACB. Then you go B, then you put A again. So, and then you just keep going, etc., etc. So you can see this lends itself to basically backtracking. It's a backtracking problem. So that's how we're going to do it. So let's get into the code. We'll need a function that we will call that tracks the current state and probably also what is used. Then our characters are A, B, and C. What's the base case? The base case is the length of current is equals to n. Then we can do k plus equals to 1 if not k, maybe counter plus equals to 1, and this is going to be a global variable, not like a counter. And then we say, hey, if counter is equals to k, we can do res is equals to current.copy, and then we have to return. Here we can say, hey, if res, if we found an answer, then we can return. There's no need to backtrack anymore. Else, for character in chars, right? If C not in used, then current.append C. Use dot add C is so that we don't. Hold on a second. No, we need to keep track of the previously used, right? So so it's not a set per se, but what is previously used? So if C is equals to previously used, continue. Else, what we do is I was thinking of an alternative method where we don't use the previously used instead, but use the last character of current. But maybe this is a little bit easier because if you use the last character of current, then you have to track whether the initial character is empty or not, whether the initial list is empty or not. So maybe this is a little bit easier. So let's wash on ahead and see in backtrack current, and what is previously used is this character and current.pop. So this is the backtracking. Now we do res is equals to empty string like this, join. Then we backtrack empty list, and the previously used is none. And then that should be good. Let's put this over here. Let's see. Oh, runtime error. Of course, my counter is 0. Oh no, res. Oh, okay. Yeah, that is fine. Res. Okay, so the code seems good. And I'm rather confident that this will work. So what is the time and space complexity of this code? Space and time complexity. So at each stage, we have 3 options, basically. Or at each stage or each level in the decision tree, we have 3 decisions, right? So we can either pick A, or we can pick B, or we can even pick C as the first character. Then moving forward, how many decisions that we have left? We actually have, we only have 2 decisions, right? Because once we pick a particular character, we can't use the character in subsequent levels. So, but then we have 2. We always have 2, don't we? I think so. Initially, we have 3 options, but once we picked the 3 options, then we have 2 options next. So from B, you can see, suppose for example, if n is, what's the maximum constraint that they give us? 10. Okay, let's say n is 10, right? Then let's just explore down this path. And from the empty string, we'll pick A, then B, then A, then B again. Then we'll pick A again, etc., all the way until all the way until the length of the character is equals to n. But from here, once we pick A, the next option that we have is C. And from here, once we pick B, the next option that we have is C. Here, if we pick C again, the next option we have is A. So you can see that every level except for the first, there's always two more decisions. So the time complexity would then be, there are always two decisions except for the first, up to n levels, right? It's up to n levels because our base case stops when the number of characters reaches n, which is basically this part, right? Of course, we also do branch and bound in the sense that once we find the answer, we do not check for uh, any other, how should I put it? We do not continuously recurse once we have the answer already. That's essentially what I'm trying to say. So we don't generate all possible guess combinations. I'm not sure if combinations is the technically correct description, but yeah, you get the idea. Once we got the K lexicographical bigger string, we just stop there. We don't do any more recursion, right? So this is the time complexity. It's the space complexity, right? The space complexity is actually the call stack. It is the call stack incurred when we do the backtracking. So you can see that there are at least up to n levels, right? Up to n levels, that means the space complexity is up to n. And oh, actually, the yeah, time complexity is still to the power n exponential. I was thinking maybe we need to multiply by the number of work done. Let's say this is the work done at each function call. Actually, the work done at each function call is kind of constant because the number of characters that we have is only 3. So we can think of it as 2 times to the power n times 3. So that is the analysis for this code. I'm going to do a submit and hopefully it passes. Okay, I guess got accepted 10 days straight, so I'm pretty happy about that. I'll just take a quick look at the editorial and see what the LeetCode team says. Yeah, backtracking. This is the one where they don't do bunch and browse, they generate all strings and check if there are at least k of them. So they generate it, they put it in happy strings, less than k, they return an empty string, and they sort it, and they return k minus 1. Let's see, n times, explore 3 options, and then 2 options, yep. This is similar to x1 orders, result in m. Thus we sort 3 times 2 is which requires, okay, I'm not gonna look at this one. Optimize recursion. I think this is the one that we have. Let's see, building on a previous approach, we will generate happy strings until we reach desired side. In the order is not random. Since we add a character in alphabetical order, yeah, correct. Yes. We can keep a counter. When we reach the cave string, we store it as a result and stop the process. Current string, the result, index in sorted list. Okay. Yep. Yep. Okay. Yep. Okay. Essentially the same idea. K times n or n. Oh, okay. In the worst case, actually that's correct. Yeah, it's correct. You might be generating the last one. Okay, fair enough. So in that case, it's still exponential. Still exponential. For each string, it performs n recursive calls, one for each character, and each of them involves only constant time, such as checking spell it. Okay. Oh, and yep. Iterative using stack. Oh, I'm not gonna look at that. Oh, okay, yeah, possibly there is a combinatoric solution. Usually this type of problem have that kind of solution, but I'm totally not good with combinatorics. So, wow, okay, your combinatorics can do an ON with a space complexity O1. Yeah, let's see. What is this n times 2 to the power n. The length of happy strings and k as the index. Let's see how they do it here. Generate happy strings, your current character in this. Or is it because of this that it's doing the ON thing? I mean, because strings in Python is immutable, if you do this, then it has to construct a new string based on the previous string with the new character added to it, and that is ON time. Did they write it somewhere? Well, yeah, I'm not sure about that one. My analysis is still what's written here, which is to the power of n, you remove the constants and the space complexity is up to ON. Anyway, that's it for me today. This is the code right here. Just gonna show it again one more time. All right, that's all. Thank you for watching and happy grinding.